When a massive star explodes as a supernova, its core may be crushed into one of two types of compact remnant, a black hole or a neutron star. Neutron stars are the size of a city, but contain more mass than our sun. They rotate rapidly, host powerful magnetic fields, and produce beams of radiation that emit a wide range of energy. When we detect pulses as the beams sweep over Earth, the object is known as a pulsar.
They can spin many times per second on their axes. The fastest pulsars spin over 700 times per second. And that rapidly spinning massive object generates extremely strong magnetic fields and accelerates particles to high energies. And we see that those accelerated particles emitting energy in the form of gamma rays, X-rays, and radio waves. And when that beam sweeps past the line of sight to the Earth, we see it pulse on, and that's why they're named pulsars.
The most sensitive tool for observing pulsars and gamma-ray light is NASA's Fermi Gamma Ray Space Telescope. Fermi scans the entire sky for high-energy sources and has found many previously undetected gamma-ray emitters. Scientists have identified many of these, but for some, the source of the gamma rays remains unknown.
I got interested a couple years ago in trying to find the limits of what Fermi can discover, how extreme these objects can be. And in order to do that, I focused on the set of objects that are relatively bright and well measured by Fermi, and found that virtually all of them have now been identified. At present, when I started this project, there were only 6 objects which we hadn't figured out what they were yet. Despite intense searches at radio, with radio wavelengths, which is the standard way in which people find pulsars, and also looking at the gamma rays themselves, no pulsations had been seen. So something was unique about these 6 objects, and I thought, that's where the discovery space is going to be. If we can track down what those are, we'll have a good chance of finding something new. We took this small set of 6 objects and attacked them with a number of wave bands, but I think the thing that helped us make the greatest progress was looking in the optical, invisible light. Now this may seem a little bit unusual for studying the high-energy gamma-ray universe, but it turns out that many of these objects seem to have optical counterparts, and if you can figure out what the visible light counterpart of an object is, you're a long ways along the track to understanding what it's all about.
It was Roger Ramani's optical observations that discovered a counterpart to the gamma ray source that showed a binary period that was indicative of this potentially being a binary millisecond pulsar.
It brightened and then it dimmed and brightened. And so this looked like we were looking at possibly something which was irradiated by a companion pulsar. And that every time you're looking at the bright face, you see a bright optical source. And when it rotates away from you and you see the dark face, you don't see anything.
We managed to get enough observations of the object to piece together its orbital period and found remarkably that it was an incredibly heated object, blue-white on one side, deep, deep red on the other, that was orbiting around something invisible with an orbital period of about 1.5 hours. Now, that's faster than any spin-powered pulsar ever known and indicates that it's a really, really tight system and that the gamma rays are blasting the companion at point-blank range. Our colleagues in Germany managed to use the orbital period that we'd measured to search in the gamma rays directly and, with a computational tour de force, managed to find the pulse signal of the pulsar directly in the gamma rays themselves.
What I'm doing is blind searches for pulsars, so that we try to find pulsars that have not been seen before. So you don't know how fast the pulsar is spinning, where exactly it is sitting in the sky. To do that, you have basically to try every possible combination of parameters if they match your data output stream. So the problem is that the number of possible combinations is tremendously high. So the straightforward brute force approach isn't possible. The computational power you would need would be in excess of what's available on the whole planet. So our work is to invent more efficient methods to do that. The basic method is analogous to zooming. It's similar to changing your objectives of your microscope in favor of one of higher magnification. So you look at one interesting point on the slide and then you zoom in on that. And then you further zoom in if it still is interesting. To find the pulsations in the gamma ray data required us about 5,000 CPU days. So if you do it on your laptop, you need 5,000 days. But if you have 5,000 laptops, you only need 1 day. And so that is the path we took, because we have a computing cluster that's called Atlas at the Albert Einstein Institute in Hanover. And that computing facility we used for this analysis, and it was immediately clear this is a detection. So it cannot be a noise fluctuation because it's so loud in the data.
A pulsar that was a strong gamma ray source, yet showed no radio signature, intrigued researchers. Among them was Paul Ray of the Naval Research Laboratory. He and his team thought they might have a solution to the puzzling lack of radio emission.
When we first discovered the system, I looked back at our archival radio observations, and none of them showed detections of this pulsar. We think that nearly all pulsars do emit radio waves. The radio beam is emitted for most pulsars from a region above the polar cap of the star, and that means it's a tightly concentrated flashlight type beam. In a system like this, where there's wind being blown off the companion star, there's a lot of obscuring material along the line of sight, it might be that it is a radio pulsar and we just couldn't see it. And the one way to confront that is to use a higher radio frequency that's more penetrating, that's less affected by the scattering in the intervening material. And so we went and made an observation with the Robert C. Byrd Green Bank telescope, run by the National Radio Astronomy Observatory in West Virginia, at a much higher frequency than typical radio observations. And it was in one of those observations that we first saw the signal from this system. And it appears that it is most of the time obscured by the material from its companion.
A combination of radio, optical, and gamma ray data allowed astronomers to assemble a complete picture of the system. It turned out to be a rare black widow binary, where a rejuvenated pulsar is gradually evaporating a low-mass companion star.
They get this name because they are in very close systems, with the companion star being close enough to the neutron star that the neutron star is irradiating the companion. So the neutron star is producing a wind of energetic particles and magnetic fields, and also all the gamma rays that are radiated. All this hits the companion star and heats it up to very high temperatures, but only on one side. So the side that's towards the neutron star gets blasted by this pulsar wind.
And it has been whittled away over billions of years to where it now is only about 8 times the mass of Jupiter.
This whole system is about the size of the Earth-Moon system, so it's very compact.
We see the pulsar at the center spinning and emitting beams of radio and gamma rays. The radio waves are represented by the green, and the gamma rays are represented by the magenta. That radiation that impinges on the star is blowing off clouds of ionized material that are collecting around the system, and that's what obscures the radio emission. So we see that most of the time, the radio, when represented in green, only makes it to that obscuring material and not through it, while the gamma rays, which are much more penetrating, go right through.
It turns out that in as far as it's a pulsar, it's not so very unusual. What's unusual about it is this binary system. And the binary system seems to have, through its history, allowed this neutron star pulsar to accrete enormous amounts of mass. The measurements to date suggest that it's very heavy indeed, and heavy neutron stars push the absolute extreme of the densest matter in our visible universe. I say this because many people think of black holes as being exotic and the most extreme objects known, but after all, a black hole has collapsed to the point where nothing is visible, it's black. A neutron star is an object that's on the hairy edge of becoming a black hole, yet is still visible in our universe. Hence, the study of these ultramassive neutron stars gives us the opportunity to study the most extreme matter in our visible universe. If this fellow is as heavy as he seems, he pushes that study to a new horizon, to a region of density and pressure which has never previously been seen.